Sequence is just a list of numbers, right? You probably knew that. And they're obviously in a special order. That's why they're a sequence and not just a random scattering of numbers. All right? And we often use a lowercase letter like A, B, or C to name the sequence. All right? They are really just functions is all they are. So they're really just functions. The domain is a set of positive integers. So you can fill that in. Again, if you have an integral right here, just scribble it out. Sorry about that. What I'm saying is that f of x and a sub n are similar ideas. So you can just write a sub n is analogous to like f of x. Okay, some quick vocab and then we'll get started. A finite sequence is a sequence with a domain that is a finite subset of the positive integers. An infinite sequence is a sequence with a domain that is an infinite subset of positive integers. A quick word on that. For example, let's say I told you that the set I'm thinking of is 1, 2, 3, 4, 5, 6, 7, ... which means it goes on forever. Right? This is an infinite subset. Subset of what? Well, there's an even bigger family of numbers called the rational numbers. It includes 2/5 and 3/5 and 18/17 and all of those numbers. So there's a huge list called the rational family, and this is just a small group of those numbers. These are the positive integers, and they are in the rational family. Okay? But it's still an infinitely long list. So it is okay to say that the rational numbers composes this massive infinite family, but the integers do too, right? Which is longer, the list of even integers or the list of all integers? Which list is longer? Which is longer, the list 1, 2, 3, 4, 5, 6, 7, ... or the list 2, 4, 6, 8, 10, 12, 14, ... They're the same length, right? They're both infinitely long, right? But clearly, 2, 4, 6, 8 is a subset of 1, 2, 3, 4, 5, 6, 7, 8. You see? So they're both infinitely long, but at the same time, one is a subgroup of the other. So anyway, that's all it means. If you see the ... you're dealing with an infinitely long list, of course. And if the list just says 1, 2, 3, 4, 5, 6, 7, and then terminates like that, and then close bracket, and there's no indication of ... then that's a finite subset. Right? It doesn't have an infinite nature at all. Sequences can be defined two ways. Don't miss these words. Explicitly and recursively, which correspond to examples 1 and 2 respectively below. Okay, I spelled explicitly wrong. It's ly, obviously. Explicitly, not ely. Let's find the first 6 terms and the 100th term of the following sequence, not followings sequence. Okay? Can I erase the ink so far? Okay, let's go to here. Find the first 6 terms. All right, so what you do on this is you would just simply plug in 1, 2, 3, 4, 5, 6. You're not allowed to start with 0 on this. The domain is always positive integers. So when you make a table for a sequence, ladies and gentlemen, don't put 0 in your table. Start with 1. And don't put 1.5. Go to 2, 3, 4. You have to start with 1. The domain is only the counting numbers, 1, 2, 3, 4, etc. Question?
And it has to be, like, is that a rule that they're only positive integers? Like, oh.
Yeah.
Wow.
The domain is positive integers for a sequence. So you're not allowed to plug in negatives or zeros or fractions.
Take that out of the video. Right up there, I didn't even read it.
No, it's okay. So if you plug in 1, you're going to get -1/3. I'm looking at this expression up here. This is sort of my function, you see. If I plug in 2, I obviously get 0 over 2, which is 0. If I plug in 3, I get 1/5. And if I plug in 4, I get basically 2/6, or you could say 1/3. And I can keep going, but I have to pick positive integers. That's the domain. Okay, this makes for an interesting plot. You plot these as ordered pairs. So 1 comma negative 1/3, 2 comma 0, 3 comma 1/5, 4 comma 1/3. But you don't connect the dots. You can't connect the dots because you're not allowed to use decimals. So there is literally nothing in between these. This is a very discrete function. It contains certain points. It is not a curve. So don't connect the dots, and don't draw anything on the left. Now, if you look at that and you compare it to f of x equals x minus 2 over x plus 2, this is a function with domain all real numbers except negative 2. So that curve is smooth, it's got two sides, it's got stuff in all four quadrants. But that's a different topic, see? But you can see they're very similar. Question?
Why is the asymptote at 1?
Because if you let LIM, if you let x go to infinity, then you get x over x being your dominating terms. So this fraction goes, eventually you plug in 100, you get 98 over 102, which is really close to 1. So it's rising toward 1. Okay, does everyone understand how the red graph is different from the black graph? Don't connect the dots, no 0, no negative x's there, just start at 1. That's how you make the tables. Okay, so I want to show you real quick how a sequence looks a little bit different from a function.
Wait, what kind of representation is that? Explicit?
Oh, that is an explicit representation. Thank you, I missed that vocab word. Explicit representation means you're actually given the function. There it is. Plug in numbers. Okay? Let's go down to this next one. Now this is a recursive representation. It'll be very obvious what that means here. What's going on is, instead of giving you a formula, I'm telling you basically what's in the list. Evidently, V1 means that V is the name of our sequence, not A. So it's V sub n. And the first number in this list is clearly negative 3. That's what they're telling us. And the next number is 2. V2 is 2, it says. But they didn't give us the third one, and they didn't give us the fourth one. But we're supposed to write the first 10 of these. We're supposed to write the first 10. So how are we going to do that? Well, what does this mean? This is basically saying, let's imagine, now that we're out here at n equals 3, let's imagine trying to find V3, right? According to this, V3 would be V sub 3 minus 1 plus V sub 3 minus 2. In other words, V3 is V2 plus V1. So just put a 3 in for n, you'll see what I mean. It means V3 is V2 plus V1. In other words, if you want the third number, you add the first and the second. That's what it's saying. It's saying the third number is the sum of the first and second number. The fourth number is the sum of the second and third numbers. The 100th number in this list is the sum of the 98th and the 99th number. Hopefully that's clear. So this is a recursive rule. It tells us how to use the first two terms to generate the third. Recursive.
Can't do implicit. Is that not what that means?
You might be able to come up with an explicit rule for this one. But I'm going to add these two together to get the next number. So what is negative 3 add 2? Negative 1, right. Now let's add the 2 and the negative 1 to get the fourth number. And then you'll add negative 1 and 1 to get the next number. Okay. Next you'll add the 0 and the 1 to get the next number. And then the 0 and the 1 again, and you'll get 1. And then you might recognize these numbers. 1 plus 1 is 2. 1 plus 2 is 3. 3 plus 2 is 5. Does anyone recognize these numbers here? These are the Fibonacci sequence. Okay. All right. So 2 is a prime number, but it is technically even, right? All right. So that's kind of a fun little sequence. Notice how it was written. It was written this way, which You know, if you really wanted to find the 100th number in this list, this formula is not going to help you do that, right? If you want to find the 100th number in this list, you know what you have to do? You got to find the first 99 numbers, because you're going to need to add the 98th term and the 99th term to get that 100th term. Tough luck. Now, if you look online, you will find a formula that will help you predict the 100th number in the Fibonacci sequence without knowing the 98th and 99th number. And that formula is online. You can find it just about anywhere. And that formula contains some very interesting things. It contains the golden ratio, which in turn is connected to E. And this Fibonacci idea, if you've ever read anything about it, it's fascinating. In this list is the golden ratio. It emerges from this list. E is connected to the golden ratio. Root 5 is connected to the golden ratio. Pentagons, human length, body lengths like arms and forearms, are buried in this number list. And all sorts of interesting things come from this list. Very, very cool. And Leonardo da Vinci, when he painted his painting The Last Supper, included a lot of golden ratio stuff in his artwork. That's why people are so fascinated with his work, and Dan Brown's nonsense book, The Da Vinci Code, was written on this premise. If you've ever read it, he doesn't know what he's talking about, but that's pop culture for you. So anyway, pretty interesting. But this is a recursive one because it doesn't give you the 100th one right away. You have to know 98th and 99th term. If you studied for like the SAT recently at all, you've probably already reviewed all this stuff. But technically, some of you may not have seen this in 2 years. Let's go to this next one, arithmetic sequences. So arithmetic sequences and geometric sequences are sort of the two most common ones that we discussed in high school, and the Fibonacci maybe. But arithmetic is just any time one number is a previous number plus something. For example, you can see here in my example 3a, I'm down here looking now. Basically, I'm just adding something each time to get the next number. Can you tell me what I'm adding each time to get the next number? What is Mr. Shore adding each time? Yeah, it's clearly a 9. Everything's going up by 9 here, you see. So basically, that's the first thing they asked for, was find D, the common difference. So you could find D a number of ways. You could try 15 minus 6. That's 9. Or you could do 6 minus negative 3. That's 9. So just take one term and subtract the term before it. It doesn't matter which terms you pick. Just pick two adjacent terms and find the difference. Because the difference never changes, we call it the common difference. Okay, so D is clearly 9. And then it asks us to find an explicit rule for the nth term. In other words, find f of x. What is the function that produces these numbers? And that is given right here. The explicit formula a sub n will always be first term plus n minus 1 times d. You'll notice this looks a lot like f of x equals f of a plus, I should say f of 1 plus x minus 1 times m. So this is really just points to the form of a line, as we'll see a little bit later in the lesson. But the first number in my list is clearly negative 3, so that goes here. N is your independent variable, so just leave it. D is clearly 9, as we found a moment ago, so this is your answer they're looking for. If you want to, you can also write it as 9n minus 12 if you like. Okay, if you want to write it as 9n minus 12, you can. Next, it asks for a recursive rule for the nth term. That's easy. It's just basically saying how is one term related to the term before it. I would say the best way to describe it is any term is the prior term plus 9. There's your recursive rule. And if you want the 100th number in the list, just use your explicit rule. 9 times 100 minus 12 is 888. Okay, question?
Yeah. I have two questions. You know how you made it 9n minus or plus 12?
No, it's 9n minus 12.
If you had that, is there a way to, like, if you were just given that, would there be a way to get it back and know what the first term is and stuff like that? Or?
Yeah. So what you have to understand is that a sub n on this problem is 9n minus 12. In other words, it forms a set of dots with slope 9 with a y-intercept of negative 12. So it's literally a line. It's a linear relation. So that would be a line with slope 9, y-intercept 12, if this was y and x. Now we're using n, so it's like a line of dots. But yeah, you certainly could find a sub 3 by just looking at this picture and finding the third dot. Or you can work backwards and find the first dot or whatever.
No, I'm saying if you had 9n minus 12, would there be a way to go back to negative 3 plus n minus 1 times 9?
Oh. How would you unravel the green to go back to this?
Yeah, is there a way to do that? If you were just given
Yeah, you could do that.
12.
What you would do is you would, let me pause the recording real quick, because I don't want it to be part of the recording necessarily, but. Random giggling on the video. Okay. Let's go to this next example. At first glance, this doesn't appear to be an arithmetic sequence. It looks like a logarithmic sequence or something, but I'm saying it's arithmetic as it says in the instructions. So there must be a common difference here. So how do you know what's being added each time? Well, you subtract. So to find the d, that's step 1, you can either take ln 28 minus ln 14, so find the difference between two terms, or if you want to, you could do ln 56 minus ln 28. Just pick any two terms and subtract them. Make sure they're neighbors, right? What do you get in both of these cases? Remember, subtraction makes a fraction. So you get ln of 28 over 14 when you combine this one. ln 56 over 28 when you combine this one. So in both cases you're getting what? ln 2. So this must be our common difference. Okay, so that was kind of weird, but that's the answer. ln 2 was our first question. What is the common difference? Next, we would try to write an explicit rule. You just take first term plus n minus 1d. That's how you do it. So you would pick the first term, ln 14, plus n minus 1d. And if you want to, you can collapse that by putting in, like expanding it out and then putting it back together. I think it gives you ln 7 plus n ln 2. Next, we're going to try to create a recursive rule. So the nth term is always the previous term plus d, as promised. And lastly, find a sub 100. And I'm too lazy to find a99 first. So I'll just go with the explicit rule and plug in 100. It's going to be ln 14 plus 99 ln 2. Where did I get the 99? It's 100 minus 1. So I'm just going back to this 2 lines back here, and I put in 100 into my explicit rule. Okay, let's go down and talk about geometric sequences. So geometric sequence. Yeah, okay, so I need to hand this out to a couple more students here. So everybody has the handout. All right, anytime you have a sequence that is changing by multiplication style, that's called geometric. So there's actually a good reason why it's called a geometric. But I don't want to get into it right now. You might remember, though, that an average is sometimes called an arithmetic mean. And in geometry, you actually learn something else called a geometric mean. So there's two kinds of averages. There's arithmetic means and geometric means. And there's arithmetic sequences and geometric sequences. So that's not a coincidence. But for now, let's just assume that you understand that geometric just means each term is a multiple of the previous term and something. So like, if you look at my example here, on example 4, can you tell what I'm multiplying by each time? It's pretty obvious. Yeah, to get the next number, you multiply by 1.5. Right? So it's especially obvious when you put this into fraction form. If you put this in fraction form, you see it's 1, 3 halves, 9 fourths, 27 eighths. If you took the time to put it in fraction form, you would see, wow, that really is multiplying by 3 halves every single time. Okay, so we have a common multiplier. So you find it just by taking any two terms and dividing them. Make sure they're neighbors. So you could do 1.5 over 1, right? Or you could do 2.25 over 1.5. Notice you keep getting the same common ratio. Okay, so I'm going to go ahead and answer the first question. The common ratio is 1.5. Check. Next it says find an explicit rule for the nth term. Find an explicit rule for the nth term. So I'll do that in blue. So it's going to be a sub n equals, and here's your form, oops, I circled the wrong thing. Here's your formula up top here. It's just first term times the common ratio n minus 1 times. So basically it would be first term in this list is 1 times the common ratio n minus 1 times. Okay, next would be, and let's do, what color do I want? I'll do black. We'll do green next. Next is find a recursive rule. So the recursive rule is a sub n equals the previous term times r. I've already determined that r is 1.5. There's my recursive rule. And lastly, in green, find the 12th term. That's just going to be the first term, 1, times 1.5 11 times. Or if you did it in the fractional form, 1 times 3 halves 11 times, like that. So how about 3 to the 11th over 2 to the 11th? You can use a calculator if you want to get that number. It's a fraction. Big number though, right? So what's going on is, this is actually really simple. If you want to find the 100th number in the list, you're going to have to multiply by 1.5 99 times. In other words, r to the 99th. That's super simple concept for you guys. Okay, so this next part, I should have drawn a line. So let's draw a line here. Okay, so draw a line right there. And these are the last two non-AP test type examples. Okay, this is just sort of background stuff. And if I can't finish example 7 and whatever else is after this, I'll just record it during my conference period next period, and you should watch it this weekend. Okay, so you know how to do the calculus part of it. Okay, so find the third term of an arithmetic sequence whose 8th term is 10 and whose 20th term is 2. I should say is 2. Okay, so when I see 8th term is 10, I think this, a sub 8 is 10. See? And when I see 20th term is 2, I think a sub 20 is 2. In other words, the graph of this sequence passes through 8, 10 and 22. And it's an arithmetic sequence, you see. And an arithmetic sequence is just a graph of linear dots, like that. So I'm just going to use any equations I know from the linear world here. Okay? So D is going to be the rise over run. Okay, look, I'll show you why. AN is A plus N minus 1D, right? So in other words, A sub N is ND plus A minus D. I just kind of foiled it out. So my slope is, this is kind of like y equals mx plus b, you see. The slope is clearly D. I should have written dn. Let me write dn so it doesn't confuse you. The slope is the common difference. The slope of these lines is common difference. So I'm just going to use my slope formula from Algebra 1 days to get the d. It's 2 minus 10 over 20 minus 8. It's negative 8/12. It's negative 2/3. Okay? So I just use slope idea to get that. And now I'd like to find the third term. So I would like to find a general formula first. Actually, let's just use a direct proportion. It's easier. I want to know what a sub 3 is. So in other words, it's 3 comma what? But it's a constant slope, right? So the ratio between 810 and 3 comma what should still be negative 2/3. So now I'm going to analyze 810 and 3 comma a sub 3. I'm just going to set up a slope for those guys. A sub 3 minus 10 over 3 minus 8. This should still be negative 2/3. And if you solve this, you find that a sub 3 is, I think it's 40/3. Let me just double check that. Yeah, 40/3. Okay, now if that example was too hard for you, there's other ways you can do it. You could play this game. You could draw 20 blanks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And you could put a big fat 2 right there in the 20th spot. And then over here in the 8th spot, just put a 10. And ask yourself, what would I have to add 12 times? What would I have to add 12 times to drop from a 10 down to a 2? Well, you're going down 8 in 12 iterations. So you're going to have to take away 8 12s 12 times to go down by 8. And then once you have your D, you can say, okay, now I'm going to go ahead and if going this way is adding a negative 2/3 each time, then going this direction would be like adding on positive 2/3 each time. You could work backwards to the third space and get that third number. So this would be a 40/3. So that's kind of a lame way to do it, but if it helps you, great. Just understand that this is a rise over run equals rise over run kind of thing too. The next one is geometric. The idea is you're given that the 10th term is 2, so you could write a sub 10 is 2, and the 16th term, a sub 16, is 256, like that. Okay? And you're looking for a2, so you're wondering what is a2. So you can write down certain things that are true. Now it's a geometric sequence. We have to use rules from the geometric list up above. Here are some rules. A sub n is a times r to the n minus 1. That's true. R is basically the n minus kth root of a sub n over a sub k. That's true. These are just rules from up above in your notes there. So let's say that you wanted to find r first. That's kind of what you do. You try to get the common ratios figured out. So what you do is you would find r by using 16 minus 10 times, or the 16 minus 10th root of 256 over 2, which is the 6th root of 128. In other words, if you write this as 6th root of 64 times 6th root of 2, that's just 2 times the 6th root of 2. Okay, and then this is 2 to the 1st times 2 to the 1/6, so that's 2 to the 7/6. So I think in class I had written 13/6. That's where I went wrong. Sorry about that. All right, 2 to the 7/6 is the common ratio. And then you can write down another statement. Let's go back to this rule at the top here. We haven't used that yet. And that's just a sub n equals a times r to the n minus 1. Let's just apply that to figure out what a is. A1. A means A1. So let's put in the r. We just found it. And let's do this when n is equal to 10, because I know A10. So let's write down A10 is a times r to the 9th. This is a true statement. And I already know r is 2 to the 7/6. And I already know A10 is 2. It was given. So basically I'm going to write this 2 to the 7/6. And this is a 9. 7/6 times 9 is 21/2. So you're going to get 2 equals a times 2 to the 21/2. and if you go ahead and divide, you get 2 to the first over 2 to the 21 halves, or 2 to the negative 19 halves. Like that. So why is this important? Because you need it to find A2. Now to find A2, you will simply multiply this once by R, because this is A1. And this gives us 2 to the negative 25 thirds if you work out the common denominator and all that. That's actually the answer. And I know it's ugly, but that is what it is. And so we started this problem in class, and I had the wrong R, so I messed up things a bit. All right, so there is your answer for that one. All right, now begin the problems that you might see on the AP test, now that we have a little background. So a sequence is, like we said, a long list of numbers, but some numbers approach a value, a specific value, as you go forward. Okay, so what we'd like to do is sort of look at an explicit rule and decide if we think that it's going to approach a certain number. Okay, so if there is a limit, in other words, if we let n get big and we basically find that the numbers in the list are approaching a certain value and getting closer to a certain value, then we'll call that limit L, and we'll say that the sequence converges to L. If there is no limit like that, we'll say it diverges. That's sort of the opposite of converges. Okay, so this first example is 7a, and it says determine the convergence or divergence of the sequence, and if the convergence happens, then find the limit. So this is a very simple thing. What we're trying to understand is numbers that are way deep down in the list. So imagine having this sequence. This sequence, if you plug in 1, it gives you 2 fourths. If you plug in 2, it gives you 4 fifths, and so on. But if you plug in 100, right, you would get 200 over 103. If you plug in 1,000, you get 2,000 over 1,003. What's going on is the numbers are numerically getting closer to 2.0. And we can show that just by using our understanding of functions and their limits at infinity. So you just choose the term on top that has the largest absolute value, so that'd be 2, and there's only one term on top. And then on the bottom, decide between n and 3, which one has the larger absolute value when you go extremely large with n. So obviously the 3 would be ignored, the n would take over. And then you reduce this problem to the simpler question, what is the limit as n goes to infinity of 2n over n? The n's cancel out, and you ask what happens to the number 2 when n goes big, and the answer is nothing. So the answer is 2. In other words, you have a horizontal asymptote. It's a horizontal asymptote calculation is what it is. Okay, now this next one, if you're doing LIM, n goes to infinity, you might want to consider turning this into a 5 halves. Okay? In fact, you might even want to write it as 3 times 5 to the n all over 2 to the n. Now, as n gets larger, the top is growing faster than the bottom. And it's not because of the 3, it's because of that 5. So the 5 to the n will eventually outgrow 2 to the n. So this is going to expand to infinity, and we would say that it diverges. So the first one converges. You would say a sub n converges to 2. That's the answer. A sub n converges to 2. The next one is a sub n simply diverges. Okay, the next one is a little bit confusing, but if you do a limit as n goes to infinity of cosine, you might want to write this as multiples of pi over 2, n pi over 2. So let's just play around with this for a minute. If n were 1, it would be cosine of pi over 2. If n were 2, it'd be cosine of pi. If n were 3, it'd be cosine of 3 pi over 2. If n were 4, it'd be cosine of 2 pi, etc. And this pattern goes on forever. In other words, our list is 0, negative 1, 0, positive 1, 0, negative 1, 0, positive 1. And this pattern goes on forever. So what exactly are these numbers approaching as we go way out to the right? The answer is we don't know. Is it negative 1? Is it 0? Is it 1? There's no one specific behavior. So we would say that this diverges because the limit doesn't exist. Okay? So this is also a divergent problem. All it really means to diverge is that these numbers do not approach any particular value. They approach 3 values. And we don't know which one it's going to end up at because we're supposed to keep going anyway. So definitely not a specific numerical answer. It's 3 answers. Absolute value of sequences. This is just a little theorem that says, let's say you're trying to understand a sequence and it's just a little too complicated. Try taking the absolute value first. If the limit comes out to 0, then you can trust that without the absolute values, if you take them back off again, the answer is 0 as well. Okay, so here's the idea. If you have a sequence like this, and it contains dots, and you're kind of confused about what they're approaching as n gets big, imagine taking any dots that are below and reflecting them up. So take all the ones that are down here that are confusing you and reflect them up above. Okay? Now if you find that this is diminishing down to 0 after removing all these ones, then you can now go back and say that the original one you started with that was confusing you also goes to 0. Okay? So this is a theorem. It's been proven. We do not need to prove it, but that is what we're going to do for this problem. So this is a fairly complicated sequence. Every time you pick an odd number, it's a negative answer. Every time you plug in an even number, you get a positive answer. So that's kind of confusing. What I'd like to do is just slap an absolute value on it and check the limit. So I'm just going to go like this, like that. And what happens is this term vanishes because that thing is providing us with a 1 or a negative 1 depending on if n is even or odd respectively. And the absolute value is going to kill off any negative ones that show up. So basically I've reduced this problem to a slightly simpler one. Don't really need the absolute values anymore. And this definitely goes to 0. And the reason is the top has a most powerful term, and that's the n squared, and the bottom only has one term, that's a 2 to the n. And 2 to the n is going to outgrow n squared right away. So I mean n squared looks like this. You're not supposed to connect it, but x squared, looks like that. And 2 to the x looks like this. And it quickly outgrows n squared. It's much steeper after just a couple plugging in. Plug in 1, 2, 3, 4, and you'll see what I mean. 2 to the n is clearly much larger than n squared is. Okay? Faster growth. So anyway, this is going to 0. And our theorem is saying that since we put the absolute values in and out popped 0 for a limit, therefore, taking the absolute values back off, like this, so putting back the little negative 1 to the n, this still goes to 0. That's what the theorem guarantees us. And therefore, we can say that a sub n converges to 0. Okay, now don't get too carried away. All I'm saying here is put an absolute value in there if you see a complicated sequence, and then try the limit. If you get 0, well, then that's also the limit of the one that had no absolute values. Okay, the next one is the sandwich theorem for sequences. And this is the last topic for sequences that you will see on the AP exam. And there was also a sandwich theorem for limits that I never went over because it isn't tested really on the AP exam. So this is just basically saying this. Let's say that you happen to know that the limit of a certain sequence is L, and the limit of a different sequence is L. And then you have a third sequence, B sub n, and that sequence contains numbers that are numerically between, okay, they're numerically between A and B, A and C, okay? You would then be certain that the limit of B sub n as n goes to infinity is L as well. It's kind of like this argument. It's actually a really simple argument. Let's say that you knew there was a function that was rising towards 1, and its name was f of x. And you knew that there was another function, let's say g of x, and you knew that it was falling down onto the line y equals 1. So both of these are approaching y equals 1 as x increases. And then you happen to know about a third curve. Maybe it's a really complicated curve, but it happens to fit right in between these. Well, the f of x and g of x will force this third function, let's call it h of x. Since f of x and g of x are both approaching y equals 1, we can trust that h of x will be forced to as well, as it gets sandwiched between the red and black curves. Okay, now first we of course have to establish that f of x and g of x are approaching y equals 1, but then h of x will have to be sandwiched to approach y equals 1 as well. Okay? So all of this is with sequences, not functions, but the only difference between a graph of a sequence and function is the domain is positive integers, so it would be a set of dots instead of these curves. But that's the idea. So what I'm going to do is just take this function here, just going to find the limit of two functions that sort of resemble this, functions that are simpler, ones I understand. Okay, and they're sequences actually. So I'm going to let a sub n be 0 over 2 to the n, and I'm going to let b sub n be 1 over 2 to the n. And the reason is, I believe that sine squared is always a number between 0 and 1. Isn't that true? Okay, so my c sub n is literally between a sub n and b sub n, for sure. Because remember, a sub n is 0 over 2 to the n, c sub n is sine squared n over 2 to the n, and b sub n is 1 over 2 to the n, and sine squared is physically between 0 and 1. So I forced this, I've created this situation for myself. And I'm trying to understand what happens as n goes big. I found the function in the middle a little too hard to work with. So I'm going to do LIM, n goes to infinity, of 0 over 2 to the n. Now what is that going to give me? Obviously 0, right? And I'm going to do the other one on the other side. The limit as n goes, just should say infinity, as n goes to infinity, 1 over 2 to the n. What does this go to as n gets extremely large? Well, it too goes to 0. So what we're saying is a sub n, kind of a lame sequence, it's just 0 all the way along. Looks like that. And b sub n is a function that's coming down like that. And we're saying that c sub n fits nicely in between it. But since both the blacks are pinching towards 0, we can trust that the blue one is as well. So after we've established that the outer limits are 0 and 0, we know that the inner function has the same limit. So the sandwich theorem would then conclude that LIM of n goes to infinity of sine squared n over 2 to the n is 0 as well. And your justification would be by the sandwich theorem using 0 over 2 to the n and 1 over 2 to the n. And that concludes 8.1.